We are Group 27, and we would like to introduce you to our work in Kaggle Kinship Recognition Challenge. Our presentation will be divided into 5 parts. We will begin by introducing the problem and providing some background information. Then, we will analyze the dataset and discuss our approach, including data pre-processing, model architectures, and the machine learning pipeline. Our task is to develop an ML model that can automatically classify kinship based solely on images of people's faces. This has been an ongoing challenge for the organization since 2010, with limitations arising from the existing dataset and the performance of computer vision algorithms. So we will attempt to develop a more accurate and reliable model. First, let's take a look at the provided families in the wild dataset. The trained dataset is divided into families, then individuals. Each families will contain some members, and each members will has at least 1 images. This trained dataset contains 12,379 images. Next is the test data. These is a set of 6,282 unlabeled images. Our task is to determine if 2 random pairs of image have some kind of kinship relation. And along with the images, there is also a relationship stable with 3,598 kinship pairs. But among those, only 3,362 pairs are valid. Now we will look at some of the distributions inside the dataset. We should see that there is a bias towards some certain families. Here we have top 20 families with the most number of people, and we can see the biggest one is F601, which is the British royal family. And for top 20 people with the most number of families, many of them are also coming from F601. And surprisingly also, the family contains most number of kinship pairs in the training relationship table. So only this family alone already account for roughly 20% of the overall data. For further analysis, we divided the trained dataset into 10 subgroups, which is identified by the first 2 characters of their family ID. For example, family F0XX will contain all families from F0 to F99. We choose this division to further seek for any anomaly within smaller subgroup of the datasets. So here are the 4 statistics that we take into consideration. They indicate number of pairs and number of images per person and per family among each group. We can notice from these 10 groups that F9 is the subgroup with the most balanced distribution on number of images, whereby in its 3rd columns, there is little to none outlier data point. The data suggests that evaluating a model on this subgroup will provide a fair starting point, since no person is significantly more important than the other. And this should wrap up our analysis. Our ML model is based on convolutional neural networks or CNNs, which are particularly effective for analyzing visual data like images and videos, particularly for facial recognition tasks. They are able to identify patterns and learn features from raw images. There are a number of CNN-based models that have been developed for a variety of tasks, but we chose to use EdgeFace and FaceNet for our project. EdgeFace is particularly noteworthy for its ability to learn complex representations of images and has achieved state-of-the-art performance on a number of benchmarks. FaceNet, on the other hand, is considered one of the most accurate models for facial recognition. It is able to map input images into high-dimensional embedding spaces, where the distance between embeddings directly corresponds to their similarity. This makes it a strong candidate for our problem. Before actually implementing the machine learning algorithms, an essential process is data pre-processing, and this processing will comprise of 3 steps. First, we split our data into train and validation sets, and decided to choose F9 as our validation subset. This will account for roughly 10% of the total images and kinship pairs in the dataset. For image selection, we select 1 representative picture per person for training due to hardware limitations. Finally, for the image preprocessing, each VGG and FaceNet requires their own preprocessing steps respectively. First, for VGG, we use preprocess input function from the Keras VGG library, which perform rescale, normalization, and format conversion on the original image. And for FaceNet, the process is called pre-whitening, whereby we centers image pixel values around 0, scales their values to unit variance, and then remove all bias from input images. With all this set, we are ready to start on the machine learning implementation. Now we would go into details about how the 2 models from the previous steps can be used for our kinship recognition problem. Here's an overview of 5 steps approach us, with increasing level of complexity after each steps. First, we starting with training from scratch, then use transfer learning and feature fusion on each respective model. Afterwards, in step 4, we will fuse the 2 models to get the best out of both VGG and FaceNet. Finally, in step 5, we perform ensemble learning by aggregating best models from all previous steps. This is to leverage their collective knowledge and achieve the highest accuracy. Before moving into the first approach, we will define some training specifications that will be followed by all subsequent methods. First is the pipeline comprising of 3 steps. In step 1, we generate embedding from input using feature extractor, which is either VGFace or FaceNet. These are called backbone models. Afterward, we will perform feature fusion, which essentially fuse all the features extracted from 2 input images in order to create a single representation. Finally, this representation will be fetched into subsequent multi-perceptron layers to perform reasoning and complete the prediction task. Regarding hyperparameters tuning, only learning is tuned because it has high correlations with other parameters. This also ensures consistency across all approaches and minimize our training times. So more details regarding other parameters can be found in the table on the right. Now without further ado, let's us move on to the first approach. Our first approach is to train both models from scratch. We should note that training complex deep neural networks from scratch requires a huge amount of data as well as computational resources. The process may take significant amount of time until it obtains any reasonable results. Nevertheless, it is still worth exploring as it can provide insights into the limitations of these models. And our results on the right indicate that both models achieved a fairly good performance at more than 70% accuracy. We also note that FaceNet slightly outperforms VGFace, but the overall performance is still not satisfactory. The second approach is essentially the same as the first approach, but instead, we now use transfer learning, which is a technique that involves leveraging the knowledge learned by a model on one task and applying it to another related task. For our case, we utilize VGG and FaceNet trained by other researchers on various facial recognition tasks and fine-tune it to make our prediction. The results show that transfer learning can significantly improve the performance of both models, and VGG now outperforms FaceNet or a small margin, indicating it's actually more suitable than FaceNet for our task. Next, being motivated by Deep Fusion Siamese network of U et al., we experimented with combining various features extracted from 2 images to enhance performance and mitigate the issue of overfitting. This process involves taking the embeddings of the 2 images and perform various element-wise operators to generate a new feature map. These features are then fetched into multiple perceptron layers as in previous steps. The results suggest this would improve the VGG models but slightly deteriorate FaceNet. Nevertheless, these embeddings are new knowledge and they will prove to be useful in subsequent tasks. Previous approach, we explored the benefits of using individual models and feature fusion techniques for kinship verification. However, relying solely on individual models may not always produce accurate results, and combining them can enhance performance. Hence, we combine the strengths of the VGFace and FaceNet models to capture both structural and discriminative information. Although the results were slightly underperforming compared to VGG alone, this approach has promising potential for future development. Our final attempt to optimize our models is using ensemble learning. Ensemble learning is a widely used technique in machine learning that aims to improve model performance by combining the outputs of multiple models. This approach is based on the idea that individual models may have varying strengths and weaknesses in their predictions. Thus, we could leverage their collective knowledge to achieve higher accuracy than any single model could achieve alone. We combined a total of 23 best-performing individual models training on various subgroups of the dataset using previous architecture. Their weightage according to respective performance is shown on the right table, and by this, we could significantly surpass the performance of all the individual models. This is our final result. The ensemble learning model from step 5 indeed achieved very good result on kinship recognition task. On the public leaderboard, we scored 91.7%, placing us equal to top 3 candidate. On the other hand, for private leaderboard, the score is slightly higher at 92%, making our model equal to the top 2 submission. After trying various approaches, we realized that utilizing other face recognition models using transfer learning will lead to good outcome on similar task. For this particular case is kinship recognition. On the other hand, we do recognize some of challenges and limitations from our works. First and foremost, performance is heavily depends on data quality, which is very limited for this specific kinship recognition task. Secondly, FaceNet was underperforming VGFace, as optimizing a triplet approach was not feasible due to computing resources. Finally, many more feature combinations could be explored, not just limiting to the 3 we have chosen. With all that, this has come to the end of our presentation. Thank you for listening.